Welcome everybody. In this problem, we're asked to find integers a and b such that 12 times a plus 7 times b is equal to 1. And the main idea is that the Euclidean algorithm can be used to find the GCD of two numbers. So in this case, the GCD of 12 and 7 is the number 1. And then there's something called the extended Euclidean algorithm, which allows you to work your way backward through the Euclidean algorithm to find integers a and b such that you can write the original numbers 12 and 7 as this integer linear combination equal to 1. The issue with the extended Euclidean algorithm is that doing it by hand is very prone to error. There's just a lot of little distributivity that has to go on. You're doing a lot of substitution, and if the numbers here are chosen very poorly, you might have a Euclidean algorithm that goes through 5 or 6 steps, and then using the extended one can be a really, really difficult activity. So what I want to show you in this video is something I came up with to simplify this type of problem. I have not been able to find it written as condensed as I'm going to do it here anywhere, so this might actually be new for a lot of people. So in this video, I'm just going to show you how the algorithm is applied, and then in another video, which I'll link to in the description, I'll give a proof that this algorithm actually does what it claims to do, because it's going to seem like magic that it actually works out. So the first thing, of course, you need to do is use the normal Euclidean algorithm. So we'll start by using the division algorithm on 12 and 7. And we say, okay, 12 is 1 times 7 plus 5. And then we get that 7 is 1 times 5 plus 2. We get that 5 is 2 times 2 plus 1. And since we got to 1, we know we found the greatest common divisor, and we can terminate the algorithm. All right, so for the purposes of finding these coefficients, a and b, here's what we're going to do. We actually can ignore everything we have here other than what we'll call the quotients, right? So normally when you apply the division algorithm, you get a quotient and a remainder. All we care about is the quotients. And I'm just going to write these quotients down starting from the bottom. So 2, 1, 1. Then I'm going to put a negative in front of each one of them. Okay, so this is all completely prescribed. I'm going to write a 1 underneath the negative 2. I will always do that every single time. I will start by writing down my quotients, putting negatives in front of them, and then putting a 1 under the leftmost quotient. All right, and now the rule is going to be this. If I have a setup of this form, so say I have a q on top, there's a quotient, and I have some number underneath, and then maybe there's some number to the left over here. Well, I won't use b, maybe we'll use some e or something. What I'm going to do is multiply up and down, and then afterwards I will add. And that will give me, so whatever is over here, this would be some q prime, the next one, I'm going to get c times q plus e. So I just multiply up and then add the number to the left. So in this case, I can multiply up and I get negative 2, and there's no number to the left to add. So I just get negative 2. Okay, now I proceed in exactly the same way. I multiply up and down. Negative 1 times negative 2 is 2, plus 1 is 3. Repeat, 3 times negative 1 is negative 3, plus negative 2 is negative 5. And now I've run out of quotients here, and so I stop. And what I claim is that the 3 and the negative 5 are precisely the a and b I'm looking for. So 3 times 12 plus negative 5 times 7. Of course, this is 36. This is negative 35, and so the sum is 1. Okay, it's just that simple. A little extra comment here, and this is something we'll prove in the next video. If I look at these two adjacent ones, negative 2 times 3, those can be used to find a representation of 1, not in terms of 12 and 7, but in terms of the next line, 7 and 5. So negative 2 times 7 plus 3 times 5, well, it's negative 14 plus 15, which is 1. And if I go one more over, the 1 and the negative 2, that will give me the coefficients for a representation of 1 in terms of 5 and 2. So I would get 1 times 5 plus negative 2 times 2, and of course that is also equal to 1. All right, so let's try one more example. This is a problem we worked on in class. So there we considered the pair 97 and 34. So we wanted to find first the GCD of this number, and then write the GCD as a integral linear combination of 97 and 34. So we'll start with 97 is equal to, well, let's see, I guess that would be 2 copies of 34, which gives me 68, and that leaves 29 left over. Then 34 is 1 copy of 29 with 5 left over. 29 is then 5 copies of 5 with 4 left over. And then 5 is 1 copy of 4 with 1 left over. Since we obtained 1, we found our GCD. So we're going to want to try to write 1 as an integral combination of 97 and 34. And you might pause here and try to do it without using the method I showed above. And you'll see it's not that you can't do it, it's just that there's a lot of substitution involved and it can be rather cumbersome. Okay, you also might try to do it using the method. Okay, so hopefully you gave it a shot. So here's what we do. We only care about the quotients, and we're going to write them down, but in reverse order. So 1, 5, 1, and 2, and then we negate all of them. Then we start with a 1 underneath. We multiply 1 times negative 1 plus nothing to the left, so we get a negative 1. Okay, then we're going to multiply negative 1 times negative 5, which is 5, plus 1 to the left, that's 6. 6 times negative 1 minus 1 is negative 7. Negative 2 times negative 7 is 14, plus 6 is 20. And so the claim now is that negative 7 times 97 plus 20 times 34 is equal to 1, which of course one can verify. Furthermore, one could also use the 6 and the negative 7, which are adjacent, to give you a representation of 1 in terms of 34 and 29. So 6 times 34 plus negative 7 times 29 will also equal 1. Or you could go to the next batch and say, well, what about negative 1 and 6? So that would correspond to the 29 and the 5. So negative 1 times 29 plus 6 times 5, well, it's 30 minus 29, that's 1. And then finally, if you wanted, you could use this 1 and negative 1, and you'd be able to say, okay, that'll correspond to the 5 and the 4, so 1 times 5 plus negative 1 times 4 is also equal to 1. And there we go. All right, hopefully this gives you a much faster way of finding what are sometimes called the Bézout coefficients. Okay, so that's what these numbers here are, and makes your life a little bit better.